Good afternoon, everybody. I'm Logan Bell. I'm currently a sophomore at Riverside, but I'm attending Lakeland through CCP. I'm currently in differential equations under Dr. Maggio. And today I'm going to share a unique puzzle, f triple prime of x equals f of x. It was shared to me by Dr. Stitz last spring when I contacted him because I was interested in joining mu alpha theta. So we know from calculus 1 that y equals e to the x is its own derivative, so that equals y prime. And similarly, we have y equals e to the negative x is its own second derivative. And then sine and cosine have a very similar property in that they loop back to themselves after exactly 4 derivatives. So I'll just put up sine of x as the example. So notice here, we kind of have these like cycles, I guess. So I'll call this 1 cycle, 2 cycle, and 4 cycle. But we kind of just skipped right over the 3 cycle. So we have 1, 2, and 4. What about the 3 cycle? And I hadn't taken differential equations yet. So I started off by just guessing and checking, and I could not find anything. It really just did not want to give anything to me. So I thought, pondered for a bit, and I came up with, maybe I can gain some insight by looking at the power series of some of these functions. So I started with e to the x, and I actually didn't need to look at any others because it became pretty clear what was happening just by looking at the power series for e to the x. So, if you recall from calculus 2, the power series, or the Taylor series of a function, is basically just turns it into a polynomial. So for e to the x, we have e to the x equals the sum, and from 0 to infinity, of x to the n over n factorial. And expanding this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So now if we take the derivative, and neat thing about power series, when you take the derivative of this, you can just take it term by term, and you'll get the proper result. But something cool happens when we take the derivative of e to the x with this power series. So the derivative of e to the x equals the derivative of this, and if we take it term by term, so derivative of 1, 0, plus 1, plus 2 times x over 2 factorial, plus 3 times x squared over 3 factorial, and so on. Well, this 2 cancels with the first factor of the 2 factorial, and this 3 cancels with the first factor of the 3 factorial. So we're left with 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So it basically just turned back into itself. And the way I like to see it is it's almost like each of these terms, when we took the derivative, just shifted down one. So we can actually think of that idea. If one derivative shifts every term down 1, then 3 derivatives will shift every term down 3. So this will go 1, 2, 3 and turn into 1, and so on. So if we just take every third term from that series, then we will have another series which will satisfy the property of being like a 3 cycle. So our 3 cycle series would be 1 plus x cubed over 3 factorial plus x to the 6 over 6 factorial, and so on. So now if you take the third derivative, this x cubed over 3 factorial will turn into 1, that x to the 6 over 6 factorial will turn into x cubed over 3 factorial, etc. So that's good, but I kind of wanted a closed form. So to start with, I looked to find an explicit representation of this using like the sum notation. And one way to do it, and this is the first way I tried, was I said this is equal to the sum, and goes from 0 to infinity of x to the 3n over 3n factorial. But I couldn't really find any way to manipulate that and get it into like a familiar form that I could represent it as a closed form. So I had to find something else. And the thing I thought, well, what if I could find a function, we'll call it f of x, which was 1 when, it should be f of n, 1 when n is a multiple of 3, and 0 when n is not a multiple of 3. Because then we could just multiply the summand for the exponential term by f of n, and we would get that result. So what kind of function is this? Well, off the top of my head, I couldn't think of anything, so I went to an easier case that I did know how I might go about solving that. And that is, we'll call that g of n, which is 1 when n is even and 0 when n is odd. And I use the fact that negative 1 to the n power is positive 1 when n is even, and negative 1 when n is odd. So we can use that fact to just kind of write it as 1 plus negative 1 to the n all divided by 2, right? Because now if n is 1, or if n is even, then negative 1 turns into positive 1, the numerator goes to 2, divide by 2 and we get 1. N is odd, then the 1's cancel out, and we're left with 0. So how can we go about solving that for f of n? Is there an analogous formula, 1 plus omega 1 to the n plus omega 2 to the n all divided by 3? So what are these terms, omega 1 and omega 2? And that's where roots of unity come in. So now just to be clear, the kth root of unity is just the solution to r to the k equals 1. And in general, the roots of unity will have the form e to the 2 pi I m all divided by k, where m is just an integer. So it turns out omega 1 and omega 2 are just the other two third roots of unity. So in this case, omega 1 we'll call e to the 2 pi I over 3, and using like the Euler's formula and turning that into a more recognizable form, we have negative 1/2 plus square root of 3 over 2i, and omega 2 equals e to the 4 pi I over 3, which is negative 1/2 minus square root 3 on 2i. So great, we've found the function, and now we just need to multiply that into the exponential sum. So this equals sum n from 0 to infinity of 1 plus omega 1 to the n plus omega 2 to the n all over 3 times x to the n over n factorial. And we can clean this up a bit. If we factor the 1/3 out, and then we distribute this x to the n term to the other terms, we have 1/3 times sum n from 0 to infinity of x to the n over n factorial plus omega 1 to the n times x to the n over n factorial plus omega 2 to the n times x to the n over n factorial. And then this, I'm running out of room. Guess I'll just keep going over here. We can separate the sums out. So we just have same thing, and we can bring this omega 1 to the n and and the x to the n together into like one exponent. So we have that. And then from here, we can recognize that each of these terms is just the original like exponential series. So we can write this as 1/3 times, that's e to the x, plus e to the omega 1x, and then the final one is plus e to the omega 2x. And that would be our closed form, but we can actually keep going again using like Euler's formula. We can expand out each of these terms. So I'll actually write, so e to the omega 1x equals e to the negative 1/2 plus radical 3/2 times x, which is e to the negative 1/2 x times e to the radical 3/2 x, which is e to the negative 1/2 x times cosine radical 3 onto x plus I sine radical 3 onto x. And then likewise, we can do the similar thing with e to the omega 2x. I'm not going to write out all the details, but this becomes e to the negative 1/2 x times cosine radical 3 on 2x minus I sine radical 3 on 2x. So then adding everything up together, we have our final solution for this particular 3 cycle is 1/3 times e to the x plus 2e to the minus 1/2 x cosine radical 3 on 2x. And another thing we can do is we can actually use this to describe what a general 3 cycle would look like. If you remember that multiplying each term by a constant won't really affect the property that it cycles back to itself. It'll just affect the derivative by the same constant. So we can take away this factor of 1/3 and multiply each of the terms on the inside by a constant factor, c1 e to the x plus c2 e to the omega 1x plus c3 e to the omega 2x. And then expanding and turning it into trig and replacing all the constants that result with just singular variable terms. We can write it as a e to the x plus b e to the negative 1/2 x cosine radical 3/2x plus c e to the negative 1/2 x times sine radical 3/2x. And that would be our general 3 cycle. And one more thing we can do before I'm done here is find a general k cycle. Turns out you can basically just do the same exact process as we did for the 3 cycle, but we have to find an analogous function like f of n, but where this 3 is a k. So 2 properties that we need to know about kth roots of unity. One is if we let omega equal e to the 2 pi I over k, then all of the other roots of unity you can describe as omega to the m, where m is an integer. And then the second property is that if you take the sum from m equals 0 to k minus 1 of omega to the mn, this equals 0 if n is not a multiple of k. Because if n was a multiple of k, then all of the omegas would just turn into 1, and that's the kth root of unity thing. And then the sum would actually evaluate to k. So using this, our analogous function to f is 1 over k times sum of m goes 0 to k minus 1 of omega to the mn. And this equals 1 if k divides n, like n is a multiple of k, and 0 if k does not divide n. And then multiplying this into the series, we have n equals 0 to infinity of 1 over k times that sum of omega to the mn times x to the n over n factorial. And we can clean this up again. If you remove out the factor of 1 over k, and then you can actually just swap the sum signs because like the bounds are independent of each other. So you can write this as 1 over k times this sum and then here we have omega to the mn times x to the n. So if we just remove that and put it as one exponent, we have omega to the m times x to the n power all over n factorial. And this, on the inside here, is just the exponential. So we have 1 over k times sum from m equals 0 to k minus 1 of e to the omega to the m times x. And then finally we can expand this out just to make it more explicit. 1 over k times e to the x plus e to the omega x plus e to the omega squared x, so on until we get to e to the omega to the k minus 1 x. And then, very similar to what we did over there, we can just multiply everything by a constant factor. So we have c1 e to the x plus c2 e to the omega x plus c3 e to the omega squared x, and so on down to c sub k times e to the omega to the k minus 1 x. And that would be our general k cycle. And that's also exactly what you would find using differential equations methods. Solving like the characteristic polynomial, and you find like the roots of unity come out to be the roots of the characteristic polynomial, and then from there you can just find the fundamental set, and it turns out to be that as a general solution.